Okay, I'm going to go through chapter 14 of the AS textbook. We've kind of put off going through it because we were hoping to be back in school before now, but I don't think we can wait any longer. So I'm going to start off with part 1, which really is just about the shapes of exponential functions. You have met exponential functions in the past. You've seen them in GCSE. You hopefully, or some of you might know what the equation of an exponential function looks like, and you might know the general shape of an exponential function. We need to go into a little bit more detail than that, but let's start with the equations. What do the equations of exponential functions look like? Generally, they are when the x is the power. So that forms an exponential function. It might be being times by an extra scalar quantity, an extra multiple. So you might sometimes see things like a times k to the power of x. Sometimes they use different letters for the k. I'm going to be using b sometimes in my explanation. B is a good letter to use because this letter here is known as the base of the function. So the B for base makes sense. What do the graphs look like? Generally, exponential graphs will look like, well, what do you think? You have a think first. Imagine one in your head. They look like this. They increase. You will have seen a lot of exponential graphs lately with all the coronavirus information. We know that if this R value that they keep talking about is greater than 1, then we get exponential growth. And that R value is just this B value that we've got here. It's the base value. And if B is greater than 1, then as time increases, then the value of y increases as well. Whereas if b is less than 1, let's draw another graph. If b is less than 1, then we will get decay instead, which will look like, well, not that wobbly, but it will look like this. And that's what we're aiming to get with the coronavirus. We want it to die out. We want less people to be infected as time goes on, not more people. So very, very, current in what we're talking about in the world at the moment. But this is going to be the maths behind it all. So we've just talked about the exponential growth and decay. This we've just said is when b is greater than 1, and this is when b is less than 1. I've just put a little cross, and they would intercept. If I drew these on the same graph, they would intercept each other at this cross. This would be the same value on each graph. What is that value? What is that value? Well, that's the y-intercept, and the y-intercept happens when x is equal to 0. And if we substitute 0 into our function here, b to the power of 0, no matter what value b is always 1. So exponential functions always go through the y-intercept at 1. That's obviously unless there's another multiplier here. So if it was a times b to the power of x, or even if there was an addition of some constant at the end, that would change the y-intercept. But in general, if it's just on its own, if it's literally just some number to the power of x, then the y-intercept is always 1, whether b is smaller than 1 or less than 1. So the next thing we need to talk about is how different exponential graphs will look compared to each other. And we need to, when we draw exponential functions, we need to consider the negative values as well as the positive values of x. I've suggested a range of -3 to 3 for this. You can go ahead and draw yourself a little table if you want. Or you can have a quick think about it. Let's go -3, -2, -1, 0, 1, 2, 3, 4, 2 to the power of x, 2.5 to the power of x, and 3 to the power of x. What values can we fill in? So what happens when x is a negative power? Well, 2 to the power of -3 is the same as, if you use your index laws, a good bit of revision here, is going to be 1 over 2 cubed. So that's an eighth. Notice it's positive but less than 1. Two to the power of -2 is 1 over 2 squared, which is a quarter. 2 to the power of -1 is a half. 2 to the power of 0 is 1. 2 to the power of 1 is 2. Then we've got 2 squared is 4. And 2 cubed is 8. I'm going to need my calculator to do this one, so I'll do that in a minute, which is because I've left my calculator downstairs. 3 to the -3 is going to be 1 over 27, which I don't know as a decimal. 3 to the -2 is a ninth. 3 to the power of -1 is a third. That's 1 again. 3, 9, 27. And I will just be back in a second with my calculator. So I've got my calculator now. Let's work out that 1 over 27 as a decimal, roughly. 0.037. Okay, 2.5 to the -3 is 0.064. 2.5 to the power of -2 is 0.16. This is 0.4. This is 1. 2.5. 6.25. And 15.625. Okay, so we can now plot all of these on one graph it asks for, as accurately as we can. You've probably not got graph paper at home, but if we did that, then we would end up with these three graphs. It's probably more likely that you will just be expected, you're not going to be asked to, in an exam, accurately sketch a graph. That's a waste of time. Everybody can type numbers into a calculator. It's not going to be a sensible thing to be asked to do. What you are going to need to know is how to spot the difference between each of these three graphs. So if you were given these three exponential functions, which one would be which? And the telltale sign is not the Y-intercept, because that's 1 every time. Just looking for my highlighter. It is the value at x equals 1. Because if we go back to the table on the previous page, when x was equal to 1, that was the base value. So if we go to the other page again, there we go, then we can look at the scale and we can see that this value is 2, this value 2.5, and this value is 3. So the red one is the y equals 2 to the power of x. The blue one is y equals 2.5 to the power of x, and the green one is y equals 3 to the power of x. That is much more likely what you will be asked to show. Here, just to discuss for a second, it looks like it is touching the x-axis. When you draw an exponential function, don't let it look like it's touching the x-axis. You should always leave a gap between the x-axis and the exponential function, because it will only reach 0 at negative infinity in this example. So you will lose marks in an exam if you show it crossing the x-axis. That would be a bad drawing. So try to show that a little gap. Obviously here it's not going through it, it's not intercepting, but it does kind of look like it's brushing it, which would only happen at infinity or negative infinity, not at like -6 or 7. Okay, I've got a second part to this, and I just want you to think about the difference that having a fractional value or a value between 0 and 1, what impact would that have on our exponential function? So can you do the same thing? Let's get a table again between -3 and 3, and draw the 2 to the power of x, but now a half to the power of x as well. You might be able to work out what is going to happen, but don't worry if not, because we're about to draw it and find out. I've already filled this row in once. That was an eighth, quarter, half, 1, 2, 4, 8, a half to the power of -3. You might be able to work that out in your head. Half to the power of -3, what's it going to be? It's 8. Why? Think about why. That's what this is asking about. I'll talk about why in a minute, but I want you thinking about why. 0.5 to the power of -2 is 4. You can probably work out the next value. 0.5 to the power of -1 is 2. This is 1. This is a half. This is a quarter. And this is an eighth. And you should notice something. Here's their graphs. Why do their graphs look like that? Which one's which? Well, the one that's increasing, the one that's showing exponential growth, is your 2 to the power of x. The blue one is your half to the power of x. The question was, what do you notice about them? And what you should notice is that they are symmetrical. About the y-axis. Oops. In other words, they are reflections of each other about the y-axis. Now, what is the other topic that talks about reflections? You should be thinking transformations of graphs. Why is this a transformation of this? Our transformations are scale factors, reflections, translations. Those are the three. Do we have one of those three things here? Well, actually we do. I can transform this function into this function with a reflection. And the reason I can do that is if we start with y equals 2 to the power of x, and I rewrite that, or we turn it into a half to the power of x, we can do that by rewriting a half as 2 to the power of minus 1. 2 to the power of minus 1 to the power of x, a little bit of index law knowledge needed here, but that's the same as minus 1 times x, which is the same as 2 to the power of minus x. Now, how is 2 to the power of minus x and 2 to the power of x related? Well, that's our f of minus x transformation. And x gets replaced with minus x, leading to, when that happens, that is a reflection in the y-axis, and which is exactly what we've got happening here. Okay, so it's really good if you can make all these different links between different chapters that we've looked at and have that running through your head whenever possible. That will really help you when little questions like this crop up. Even if they don't ask you about it, even if it doesn't end up cropping up in that question, it's really good for you to kind of extend your knowledge and keep thinking back to other topics whenever you can. Having that kind of approach will really help you when the maths gets harder later in year 13. Okay, so what I'm going to do is stop there and let you have a look at exercise 14a. You should now have done enough prep to work through exercise 14a. It's a lot of graph drawing, I'll be honest with you, but that should help. As always, if you've got any questions, send me a message on Show My Homework, send me an email, or leave a comment on my YouTube channel. I'll see you soon.